Hello everyone, my name is Silvio Perez and I'm an application engineer here at Hawkard Systems. In this video I'll be running through the great enhancements for SOLIDWORKS Simulation 2015. In this first example here, we want to run a nonlinear analysis on this cap insert. So what I did to define the nonlinear analysis, I actually created a 2D simplified version of this model. So the new functionality that was introduced in 2015 is that when we run the results, we now have the option to show the intermediate results up to current step. This feature is similar to flow simulation and plastics, more so because we can see our results in real time. So this is definitely a great feature to be able to see whether things are moving in the direction that you're expecting, where you no longer have to wait until the study completes to see that your bodies are now not behaving as expected. So definitely a time saver in that regard. A new functionality has been added to 2015 as well, called the Load Case Manager. So if I go and reference the static analysis here, to access the Load Case Manager interface, we just have to right click on the study name and we see that we have the option there. So if I go into the Load Case Manager, what that allows you to do is to create different load conditions. So in this scenario, you define your study like you would normally, but then you may be interested in how these different load conditions that we define, how they change as a different load value, a certain direction there. We can even suppress that condition as well. We can also filter out whether we want to show any of the fixtures or on the load conditions there, or any of the contacts or connectors, or we can show anything else. But what this pretty much allows us to do is to create different scenarios in a table format. So you see that we have a color code here on top that kind of correlates to the load condition that we created. So if I add a new condition here, I can name this whatever I like. I'll call it torque. And you see that it's a new condition that I've added to this load case scenario. I can say that instead of having it suppressed, I actually wanted to output some sort of value for this, in this case 50 Newton meters. I can also correlate and combine these load case conditions here by selecting some kind of like equation. So I can say that the 20G vertical load here, we can make a relationship with the torque that we created by setting up some kind of equation here. And we can see how the relationship between those load conditions are interacting now. So if I define that interaction, you see that the last thing that we can do is create some kind of result. So we want to know how these load conditions affect any potential stress or any displacement that's being applied to this model. And in this case, you add that by defining sensors. So after you define your scenarios, you can then run the analysis, and if I switch over to my completed file set here, we can go to our results view. And you see that the results that we see correlate with the sensors that we've defined. And you see that it produces those values based on those different load conditions. So it's definitely a great way to eliminate you having to create individual studies or potentially utilize the design study module to be able to see all the different load conditions that you may want to apply to your model. If I switch over to my dynamic name study here, we actually ran a harmonic study. And like normal, when you right click on your results, you can define the response graph. And that's a great graph to see, to be able to see the response, let's say the stress as a function of frequency. But this may be a little bit limited as far as maybe you want to know the direction in where things are being excited. So now what SOLIDWORKS introduced was, if we right click on our folder results, we can define now a frequency response graph. And what that allows us to do is see the effective mass participation factor or the accumulative effective mass participation factor. So if I select that option there, you see that if I output that graph, you can see the different directions in which things are being excited as a function of frequency. We also have the functionality here to specify the cumulative, which is just the combination of all the different modes, and we see in this case that the z direction is the main contributor. So definitely being able to get a lot more information here with your harmonic study. Now, if we wanted to run a fatigue study, we're no longer limited to reference a static or nonlinear analysis. So you see that if I were to create a new fatigue study here, we have additional options. So if I hover over these different options here, we see that we can now reference a harmonic fatigue study or a random vibration study. And that's actually what I define here in this file set. So if we take a look, I'm now referencing that dynamic analysis. So if I edit the event here, you see that it's now referencing that analysis. We can say what plot step we want to reference and then how many cycles we want to run this for. And then we get the normal plots we would get in a fatigue study. So now again, we're not limited to just a static or nonlinear analysis. We now have expanded more options for you in terms of referencing our harmonic or a random vibration study. In the situation where we need to define a lot of shells, it can become a little tedious to have to individually define each cell definition by normally right-clicking on that component and specifying that definition. Now in 2015, they've kind of made that process a little bit more efficient. So if you right-click on one of your bodies here that you want to define as a shell, you see that we now have a shell manager option. And what that brings up here is this interface here. And we have a few things to set it up. So on the left-hand side, we see that we can individually define the shell like normal. Specify some kind of face or some kind of surface body, define whether we want a thin or thick element, and the offset, and of course the thickness of that shell. But in this case, what SOLIDWORKS 2015 does is it recognizes all the shell bodies for you and imports it into this interface. In this case here, I've already set up a few things already. But what we have available to us is that you see that we have a lot of shell bodies that share the same size. So if I click on one of these pull-down menus, you see that we have the option here to manage groups. And these correlate with the names that I've defined here already. So I've specified some group names already by typing in that group name here. And we can say that for this specific group, I want it to be a thin shell. I could specify a material if I wanted to, and of course the thickness of the shell. So in this case, note that the base lateral group here all have a shell definition of 5. What makes this tool really efficient and great is that I can just change the value in this interface here, let's say to 8, and then hit OK. And then all the base lateral conditions should be updated here. And let me try that again and make sure I'm selecting the right group here. So again, base lateral, let me change this to a value of 8, hit OK, and all those values get changed as well. We don't necessarily have to go into that interface either. We can click on that individual value, change that back to 5, and when we hit enter, all those values, all those shells that are under that base lateral group here get adjusted. So again, it's a great way to simplify the process of defining these shells. Of course, in this scenario here where we do have a lot of shells, we may want to know where those shell bodies are located. You know, before we would have to go into our simulation tree, click on that body and see what highlights. But now we have these filters, such as we can filter the thickness here, and it automatically generates a color code. So you see that the colors correlate here with the model and this area here at the bottom here. So everything that's classified blue, green, yellow correlates with the model here. So it's definitely a great way to be a little bit more organized, be consistent with what faces you're defining as a shell, and eliminate some of the tedious process that is behind defining these shell elements. Lastly, in this example, we have a string model where based on the loading condition, we want this face to come in contact with each other. If we wanted to define the contacts for the touching faces here, normally what we need to do is kind of create a split line feature here to specify where those contact faces are located. So this is more generally a problem when you have these swept features or any lofted features kind of similar to this model here. So all we need to do here is when we define our contact set, you see that we have a new self-contact option. So when we select that option, all we need to do is select the single face here on the body where we know that there's going to be self-contact. So if I define that property like what I've done here, so in this example, right? So we see that we no longer have to specify the split line features. It recognizes that we've defined that there's going to be contact within that single face. So when we run the result here, we can get the result, same accurate result, without having to do the extra step of modifying our geometry. In this video, we saw some of the top enhancements implemented for SOLIDWORKS Simulation 2015. Thanks for watching.